Welcome to the first virtual session of this fall semester. Speaker today is Professor Yashwant Borse from Pune University. Thank you for being a speaker today, and please have the floor.
Thank you. So, shall I start?
Yes.
Okay. So, thank you very much, Professor Sandra Kingan. I'm really pleased to give this seminar here in New York Combinatorics seminar. I think I had received this invitation in in February. I think it was the end of the seminar sessions of last semester, or what you call it is a fall or winter, I don't know. But so at the beginning of this new semester, so I got this chance. So I'm very much thankful to the organizers, all the organizers, this group actually, for inviting me for this seminar. Okay, so topic of the seminar is decomposition of the hypercube, or one can say hypercubes. So I'm a professor in the Department of Mathematics, Savitribai, Phule, Pune University, India. And okay, so let me first talk about the outline. Okay, so outline of our talk is first preliminaries. So what is decomposition? We will talk about. Then we will introduce hypercube. And then there are 4 types of decompositions which have been studied or being studied for hypercube in terms of decomposition. That one is a tree decomposition, other is Hamiltonian cycle decomposition, third smaller cycles, decomposition into smaller cycles, and the fourth one is decomposition into regular spanning subgraphs. These are more major areas in which decomposition of hypercubes is usually studied. There are other areas also where people study decomposition into stars, into different types of subgraphs also, but these are standard areas or classical areas where people have started working, and they have there were some open problems and people tried to solve them, sometime fully, sometime partially. There are some conjectures. We will discuss all these things here. Okay, so decomposition. So a decomposition of a graph G is a list of edge disjoint subgraphs H1, H2, say Hk of G, such that the union of these subgraphs is equal to G. So basically, it is edge partition of G into subgraphs. So each part, so ith part gives you ith subgraph, say Hi like this. And if this H1 to Hk gives you decomposition, we say G is decomposable into these subgraphs H1, H2 up to Hk. And suppose if all Hi are isomorphic to H, single graph H, then we say G has an H decomposition. So G has an H decomposition if it has a decomposition into copies of H. So given a H will be given, and people will ask whether the graph has decomposition into H or not. So for example, so this is a graph G on the left side, and I think on the right side there are 2 H1 and H2 subgraphs of G, and we have decomposed G into this H1 and H2. See, the H1 and H2 are edge disjoint and their union is G. So G is decomposed into H1 and H2 here. Okay. This is another example. P4 is a path on 4 vertices. So look at this graph on the left side. In different colors, we have given here decomposition of G into copies of P4. So this is blue, gives you one copy of P4. From there, another color here is another copy. This is third, and this is fourth. I think so. This G can be decomposed into 4 copies of P4. So this decomposition is shown here using different colors. Now, hypercube can be defined through Cartesian product of graphs. So the definition of Cartesian product of graphs is like this. Suppose G1, V1, E1 and G2, V2, E2 are 2 graphs. Then the Cartesian product of these 2 graphs we denote by G1 box G2. It is a graph with vertex set V1 cross V2. Cross means this Cartesian product of sets V1 and V2. And 2 vertices Ux and Vy. Ux and Vy are adjacent in the product if and only if U equal to V means the first 2 are equal and the second thing is that is X and Y forms an edge in E2, or the second coordinate that is X equal to Y and the first coordinate that is U and V are adjacent in E1. So with the help of figure, we can understand it easily. So suppose consider the Cartesian product of the graph C3, which is triangle, and the path P4 on is a path on 4 vertices. So what we have to do, replace each vertex of path by a copy of C3, right? And then so replace these 4 vertices by these 4 copies of C3, and then put the edges. Suppose X is adjacent to Y, then put the edges between the 2 copies corresponding to X and Y. Similarly, put the edges between the copies corresponding to Y and Z. Similarly, Z and T and so on. So this is the way. Or alternatively, you can replace vertices of C3 by the paths and join those copies of paths by edges corresponding to these edges UV, VW and WU, like this. So this is sort of replacing a vertex of one graph by a copy of other graph. And 2 vertices are adjacent in second graph, then make all vertices adjacent to the corresponding 2 copies of the first graph. Okay. So now I define hypercube. So here we will use n everywhere. So n will be a positive integer. So it will be greater or equal to 1. So the hypercube Qn is the graph obtained by taking the Cartesian product of complete graph K2. How many copies? N copies. So Qn is K2 product K2 product dot product K2, and how many terms are involved there? N terms. So it is the Cartesian product of n copies of K2. So there is a definition of torus also. The Cartesian product of cycles is, suppose there are n cycles, so Cartesian product of n cycles is generally called as n-dimensional torus. So if n is even, then Qn can be written as Cartesian product of 4 cycles. How many? N by 2. Because K2 product K2 gives you 1 C4, right? If there are n K2s, then there are n by 2 C4s. So Qn is also the Cartesian product of C4s, n by 2. So you need n even there. So thus, hypercube is also a sort of special case of torus, or the torus or the Cartesian product of cycles is sort of generalization of the hypercube Qn. Okay, so thus Qn is a torus for even n. So these are the examples of smaller hypercubes. This Q1 is just one K2. Q2 is K2 cross K2, means this is two copies of K2 joined by this perfect matching. Then, okay. So two copies of K2 joined by perfect matching. Then Q3 is obtained by taking two copies of Q2 by joining by this perfect matching is shown by this black edges, right? And Q4 is obtained from two copies of Q3 by joining the corresponding vertices by a perfect matching this way. So Qn is obtained from two copies here. So for example, you have this Qn minus 1 and this another Qn minus 1, and then suppose this is Qn minus 1, this is Qn minus 1. Then you join corresponding vertices by a perfect matching. So this is perfect match. This way you obtain Qn from two copies of Qn minus 1. Okay, so this is generally the structure, and this is the important structure. So this allows us many things. One is recursive approach. The second one is to use this Cartesian product properties and induction and many things. So we can use this definition for three purposes: induction, recursive nature, and many other things that we will see in the proofs also. There are two alternate other definitions I'm giving here. One is write down this set n as set 1, 2, 3 up to n as this n, and the power set of this. So you can label the vertices of hypercube Qn with the power set of the set 1, 2 up to n. So this is n element set. So the power set of it has 2 raised to n members. So the vertex set of Qn has 2 raised to n members, and two members A and B are adjacent in Qn if the symmetric difference of them is a singleton set. So currently it is 1. Means singleton 1 will be adjacent to, say, empty set, for example, and 1 will be adjacent to 1, 2, kind of this thing. So you take the symmetric difference of A and B. So A and B should differ only in only one position. So they should have in symmetry difference should have a singleton set. This is important condition here. Another condition, another way we can define hypercube as this. So take vertex set as Z2n. Z2n means Z2 cross Z2 cross Z2, n copies. So this is a binary strings of length n. So the vertices of Qn are all binary strings of length n. So there are such 2 raised to n strings, and 2 strings are adjacent if and only they differ in only one position. So these are 3 different approaches of Qn. One, it is a Cartesian product of K2, n copies of K2. Second, its vertex set is power set, and the adjacency is relation defined through symmetry difference. This is and this is a one approach is binary string approach. Now we go to the properties of Qn. So it is a very fantastic graph. It has 2 raised to n vertices as seen earlier. It is an n regular graph, and therefore it has n into 2 raised to n minus 1 edges. So large number of vertices and large number of edges. Connectivity is n, means vertex connectivity as well as edge connectivity n. Fantastic graph. Still diameter n. Though it has 2 raised to n vertices, still its diameter is very less, that is n. It is a bipartite graph. It doesn't contain any odd cycle, only even cycles. It is bipancyclic. Bi means even, pan means all. So it contains cycles of length 4, 6, 8 up to 2 raised to n. So for every even integer L from 4 to 2 raised to n, there exists a cycle of length L in Qn. So that is considered as bipancyclicity property of Qn. And recursive nature, as said earlier, Qn can be written as the product of Qn minus k and Qk. Okay. And this is a highly symmetric graph. So there is a symmetry in vertices, edges. So vertex transitive, edge transitive graph. And because of all these beautiful properties, this Qn is considered as one of the important interconnection networks. So in interconnection, in parallel processing, generally this interconnection network is processes and links. The processes are represented, this interconnection network is represented by a graph, where processes are represented by vertices and links represented by edges. So in which way we should put the processors and should join the processors through links? So what topology we should use? So the one of the best topology is Qn. Why? Because we want many number of processors to put, still the communication should be faster. So diameter of corresponding graph should not be more. So it is still n. Further, it should be symmetric, and some beautiful other properties are available. So recursive nature is one of this good property, and bipancyclicity, that so many cycles you can create in Qn. So because of this beautiful property, it has been used as one of the important interconnection networks of parallel computing. Okay, so there are variations also. So torus, for example, is one variation. Augmented cube, I think it is augmented cube. There is some spelling mistake here. So, and there are many other, but these are some standards. So I told you that torus is the Cartesian product of cycles, and Qn for n even is also Cartesian product of cycles of length 4. Similarly, augmented cube is some variation where degree is 2n minus 1 and dimension is also less than n. So we will not go into details of these variations. Okay, so we will focus on now decomposition. So history. Earlier, decomposition of the complete graph was considered. So in 1847, Kirkman tried decomposition of Kn into triangles, and in 1891, Wallecki gave decomposition of Kn into Hamiltonian cycles. This construction of these cycles is given in Alspach's paper that we will see. And then decomposition of Kn into cycles of, say, equal length. This research was going on for a long time. Then there was another problem, that why not to decompose Kn into cycles of different lengths. And this problem was also researched for a long time, and I think it's finally settled in 2040. So So now cycle decomposition of Kn, I think this problem is over. There are books on decomposition. So there is one book is by Borse, it is 1990 book. There are surveys. So this survey, this 1985 survey is on factorization. Means factor means spanning subgraph. Factorization means decomposition into spanning subgraphs. There is another survey which talks about factorizations, and it records the development on this topic from 1985 to 2003. And just I said this is a paper. This is a survey by Aspect, Vermont, and Sato on Hamiltonian decomposition of graphs. And this paper gives you this construction of decomposition of Kn into Hamiltonian cycles. I was motivated by this last paper, and because I read this paper, and then later on I started working on decomposition. Okay, so it's a famous conjecture in graph theory, I think in mathematics also. It is called Ringel's conjecture. It says a complete graph K2n plus 1 decomposes into any tree of size n. Size means number of edges, right? You take any tree with n edges, this complete graph can be decomposed into copies of that tree. This is simple, straightforward conjecture. One may say it is so easy, right? So anyway, so people have converted this conjecture in terms of labeling also. Graceful labeling. I think in every graph theory book, our standard graph theory book, this thing is given. Graceful tree conjecture. It says that every tree has a graceful labeling. There is some labeling, not giving you definition of graceful labeling here, but this is more general conjecture than this Ringel's conjecture. Both conjecture are still open. So people tried this conjecture for different class of graphs, and one of the standard class, as you said, Qn, hypercube Qn. So Pink in 1990 proved the hypercube version of this conjecture. Similarly, Jacobson et al. Independently proved the same conjecture for Qn. So we will see the proof given by Pink. It's a fantastic small proof, but idea is so nice. See this. So this is theorem by Phule. Qn, hypercube Qn decomposes into any tree of size n. Okay. So let T be a tree with n edges. Label the edges by singleton 1, singleton 2 up to singleton n. See, I am using here the vertex set of Qn as the power set of 1, 2, 3 up to n. So my vertices are sets, subsets of 1 to n, right? So I'm labeling the edges by singleton 1 to singleton n. There are n edges. So choose a root R in this tree T. Any vertex you can consider as a root and call it R. Label the root by empty set. So I have not written here, but label the root R by empty set. And now for any vertex X in T other than R, there is a unique Rx path. Look at all labels. Look at the labels on this path. Look at the labels of all edges on this unique Rx path. Collect that labels, make a set, and give that set as a label for X. So label of X is the set of all labels of edges on the path R to X in T. So this way you get label for X, and thus T is embedded in Qn. Thus T is embedded in Qn. Now we want Qn to be decomposed into copies of T, right? So what we are trying now, we will apply a subgroup of automorphism group of Qn on this T to get different copies, so that all those copies together will decompose Qn, right? So see, for a subset of, this is not vertex set of Qn, actually say this is A belongs to vertex set of Qn, or you say a subset of 1 to n. So this is belong to notation, right? Then define rho A. This is rho A is a automorphism from vertex set Qn to vertex of Qn. So rho A of x is equal to the symmetric difference of A and x. This is automorphism induced by A. And look at this subgraph G of automorphism of Qn. This rho A when mod A is even. So this G is a subgroup of automorphism of Qn. And now take this collection. Apply this rho A on T. T is a tree. Rho suffix A is automorphism. So the image of T under this is also a tree. And how many members this group G has? All those fellows, when you apply on T, you get disjoint trees. So I'm not proving here disjointness, but they are all disjoint. Now this collection C is a collection of disjoint trees, which are disjoint copies of T, and all these copies together decomposes Qn. So the idea is simple, to embed T in Qn and apply a subgroup of automorphism group on T. So this subgroup is this G, defined like this. So applying group, they have got decomposition of Qn into copies of T. Similar idea is also used for other kind of tree decomposition that we will see now. So before that, now Qn is decomposed into tree of size n. Okay, why tree? Why tree? Why not another graph of size n? So Ramras in 1991 proved that Qn can be decomposed into any connected subgraph with n vertices and n edges. So it is a unicyclic subgraph. So it should be a subgraph, right, of Qn. Otherwise, you can't decompose it. For tree, there was no problem, because they proved that the tree with n edges is a subtree, or say it can be embeddable into Qn. So there was no issue. But for general graph, you need to have it first subgraph. Otherwise, you can't decompose it. Another generalization. So this is a conjecture by Horak, Siran, Wallis. Qn decomposes into any subgraph of size n. So this conjecture they proved for the special case when subgraph H of size n. So when every component of H is an edge or an even cycle, under this restriction, they have proved that Qn can be decomposed into copies of H, where H is a subgraph of size n in which each component is H or an even cycle. But in general, the conjecture is open. There is more general conjecture than this by Graham and Hadwist. Every 2n regular graph decomposes into any tree of size n. Now we are not talking about K2n plus 1. This is a complete graph. Now 2n regulars is more general than Ringel's conjecture. So this is still open. I think for stars or for double stars, this conjecture has been proved by proved in some papers, but this is still open at a large extent, wildly open conjecture. Now we will talk about we have just seen decomposition into any tree of size n. Now think of just think of a size, larger size, say size 2 raised to n minus 1, almost half the size of Qn, right? So Wagner and Weil consider the decomposition into a tree of large size, size 2 raised to n minus 1. They constructed such a tree, say Tn, that decomposes Qn. Their construction I am giving here. The vertex set of this tree Tn will be the power set of n minus 1 union this singleton, this vertex, that is n. So this is the full set. This is a full set. This is a 1, 2 up to n. So take this fellow as a root, and for x different from this, for x assign parent px such that the parent is x union the integer which is a minimum integer not belonging to x. So let us see this construction here through example. And the age will be there between x and px, where x is subset of n minus 1. So this single, this for example here, 1 is a parent of empty set. Here for T2, so you have n equal to 2. So this set is 1, 2. So empty, 1 is a parent of empty and 1, 2 is a parent of 1. So this is your T2. For T3 now it is interesting. So empty is adjacent to 1, then 1 and 2 adjacent to 1, 2, 1, 2 is adjacent to 1, 2, 3, and this is the final one. This is the root. Okay. So this is the tree T3. Similarly, one can define T4, T5 up to Tn. And this Tn has 2 raised to n minus 1 edges. Now we apply a subgroup of automorphism group on Tn to get the decomposition of Qn. So consider the permutation of 1 to n. This is a cycle. And now apply this pi on T. So T, pi 1 T, pi square T means 2 times you are applying pi on T, and so on up to pi raised to n minus 1 T. So this, they proved that, Wagner and Weil proved that all these copies of T are edge disjoint. So we have such n copies here, and each copy has 2 raised to n minus 1 edges. So total n into 2 raised to n minus 1 edges are exhausted by the members of C. And these are, so Qn also has n into 2 raised to n minus 1 edges. Thus, all edges of Qn are exhausted by these copies of C. Therefore, C is the collection of edge. So C gives decomposition of Qn into copies of T. T means Tn here. See, T means Tn. That Tn we have constructed. That Tn is there. So see the illustration. So this bold one. So this T3 is denoted by solid edges, and then pi T3 denoted by bold edges, and for a third copy is denoted by dotted edges here. So Q3 is decomposed into 3 copies of T3. This decomposition is given here. Just spanning tree decomposition. Now tree with n edges, tree with 2 raised to n minus 1 edges, and now tree with 2 raised to n vertices spanning. So Qn can have at most n by 2 disjoint spanning trees. This comes from the number of vertices and edges of a spanning tree. So Barden in 1999 proved that Qn is decomposable into n by 2 spanning trees and one path. Yes, every time -1 is there. So the n by 2 edges will remain, will not be covered by the spanning trees. But the problem with the theorem is that, and this is for even n, this is for even n, the trees constructed here may not be isomorphic. In fact, they are not isomorphic. The specific construction is given and the trees are not isomorphic. So one can try isomorphic spanning trees to decompose Qn. So this thing is open here. So this is all about tree decomposition. These are the three major theorems. One about tree with n edges, one about 2 raised to n minus 1 edges, and one about spanning trees. Right? So the decomposition of Qn into trees of size different from this problem is completely open. What about path? So to get the decomposition of Qn into path Pk, what we need is that this Pk here, Pk means this K means number of edges in path. So I should have here Pk plus 1 actually, right? So number of edges of path should divide the number of edges of Qn. So this is actually, otherwise we have to say that Pk means a path containing k edges, or I should write down here Pk plus 1. Okay. So K must divide n into the total number of edges n into 2 raised to n minus 1. So Faraday proved that Qn can be decomposed into path of length k if k is less equal n and k divides n into 2 raised to n minus 1. See, please read Pk as path of length k just now. So it is not inconsistent with my previous notation, but here I am considering like this. But for odd n, whenever n is odd, k automatically becomes less equal n if you want to get decomposition. This is obvious necessary condition. But for even n, there is no condition, such condition on k. So just the condition is that k must be less than 2 raised to n and k should divide n into 2 raised to n minus 1. So Qn is decomposable into path of length k for any k less than 2 raised to n and k dividing n into 2 raised to n minus 1. This is a conjecture by Faraday and open from 2014. Decomposition into Hamiltonian cycles. This is very interesting and classical problem. So Ringel in 1956 constructed Hamiltonian cycle decomposition of Qn when n is a power of 2. Construction is given, but not for all n, when n is a power of 2. And asked to find such decomposition for general n. The attempts were made to find Hamiltonian decomposition of Cartesian product of cycle. So it is Cartesian. So this spelling mistake here. Cartesian product of. So Korzik did it for 2 cycles. So Cartesian product of 2 cycles can be decomposed into 2 Hamiltonian cycles, he proved. Fourier extended this result for 3 cycles. Hubbard and Snyder proved this important theorem where it says when G is 4 regular and Z is a cycle and G is decomposable into 2 cycles, C1 union C2, then G product Z is decomposable into 3 Hamiltonian cycles. So there is a condition on G that it is a 4 regular and decomposable into 2 cycles, right? So C1 union C2 product Z gives you 6 regular graph and it can be decomposed into 3 Hamiltonian cycles. This is an important result. So using this, Alspach et al. Proved this as a consequence of these results that Cartesian product of n cycles has Hamiltonian decomposition, means decomposition into Hamiltonian cycles. It's very important result. And it follows easily from the result of this Aubert and Snyder. It is proved in this paper. And as a corollary, for even n, Qn has a Hamiltonian decomposition. That is decomposition into Hamiltonian cycles, right? So Hamiltonian decomposition is over, and then problem started decomposition into smaller cycles, right? So say CK decomposition. For CK decomposition, CK has length K, so K should divide the number of edges of Qn, that is n into 2 raised to n minus 1, right? So the question is, for which K dividing n into 2 raised to n minus 1, does there exist a CK decomposition of Qn? So let us see the early result. So Ramras in 1991 proved that CK decomposition is possible when K is small, that is n. Then Zanati and Eindon proved that if K is power of 2, then CK decomposition is possible. Okay. Now, when K is a power of 2, job is over. Now, what kind of K will be now? N into power of 2. So, K equal to n over. Now, 2n, 3n, 4n, this type of 2n, 4n, 8n, 2 power into n. These kind of Ks are now remain. So, Mollard and Ramras consider the case of K equal to 2n, and they constructed a nice cycle of length 2n. So, the cycle with initial vertex phi, age direction sequence 1 to n, 1, 2 up to n, and again 1, 2 up to n. So, this is a cycle of length 2n. Apply this rho A on C, where A is a subset of 1 to up to n minus 1, and commutative of A must be even. So this rho suffix A is automorphism. So it gives you copies of C again. And it is proved that all these copies are edge disjoint, and they together decompose Qn. So again, this C or this rho A thing, that to get all these A's. So here you are getting a particular cycle C, and we are applying a subgraph of automorphism, subgroup of automorphism group of Qn on C to get different copies of C to decompose Qn here. But the problem of 4n, 8n and all to power t into n is open. So we tried it in 2019 for 4n. I think we also tried for more general n, but I'm just giving a proof of 4n here, some idea. So in fact, we proved a stronger result than this, that Qn decompose into 4n cycles. So stronger result is that Qn can be decomposed into 4n cycles, C1 to Cs, whereas equal to 2 raised to n minus 3, satisfying. The cycle also satisfies the condition that Cj contains matching Mj consisting of 4 edges, such that every component of Cj minus Mj is a path of length n minus 1. And all these matches together gives a perfect matching of Qn. So we have cycle C1 to Cs. Each cycle contains some matching with 4 edges, and all this matching together gives you perfect matching. Further, when you delete a matching from Cj, you get components, and those components are paths of equal length. The length is n minus 1. So we have proved this using induction. So it is easy to check for n equal to 4. Assume that n greater than 4. We have assumed n even in the statement. So the next even fellow is n plus 2. So write down Qn plus 2 as Qn product Q2. Q2 has 4 vertices. So this Qn plus 2 splits into 4 copies of Qn, say Q1, Q2, Q3, Q4, where 1 and 2 are adjacent, 2, 3 are adjacent, 3, 4 is adjacent, 4 is adjacent to 1 through matchings. And now by induction, each copy, this Q1, Q2, Q3, Q4 decomposes into cycles, say CGP, and these cycles contains matching as stated earlier. Now using the cycles CJ 1, 2, 3, 4, we construct new cycles like this. So subtract the matching from that CJP and replace this matching of this cycle by the matching of the next cycle. This MJP plus 1 is the matching in the cycle CJP plus 1, and use this cross edges FJP, cross edges. So edges between the copy Q1 and Q2 corresponding to the matching end vertices of this matching. See this figure. So this is CPJ, this is CP plus 1J. These are matchings, matching of CJ, CPJ. This is a matching of C plus 1J. I am replacing this matching of this left copy by the matching of right copy and this cross edges. This way, we get a new extended cycle, say CPJ, and all these cycles together decompose Qn plus 2. So details can be provided, but this is the idea, that use cycle, remove matching, replace this matching from the matching of next cycle, and continue like this. So this is the idea we have used to prove this. Now Fourier cycles, okay? So decomposition into Fourier cycles. And in 2021, this paper come, I think Professor David Opner is here. So it is his paper that Qn decomposes into K cycles when K divides n into 2 raised to n minus 1 here. So it is not n, 2 raised to n. This is 2 raised to n minus 1. And this K is less equal to 2 raised to n divided by n. So this covers most of the cases. But still problem is not completely solved. Most of the cases of K are covered here, but still problem is not completely solved, right? Okay. And now this is decomposition into spanning regular subgraph. Now tree over cycles over spanning subgraphs, factorization, factors. Okay. So Borse and Sudborough considered a decomposition of Qn into spanning regular connected subgraphs. They were motivated by applications in fault tolerant computing and construction of adaptive routing algorithm. So what they propose? They propose this problem in 2003. Suppose n is multiple of m, say n equal to mk, and k get equal to 2. Does there exist a decomposition of Qn into m copies of a spanning k regular subgraph with diameter n? M copies of a spanning k regular connected, also we can assume, connected subgraph with diameter n. And they solve this problem for m equal to 2, where they decompose into a spanning 2 copies of a k regular connected spanning subgraph of diameter n plus 2. Okay. But see, Hamiltonian decomposition of cycles or Qn says Qn can be decomposed into, for even n, can be decomposed into spanning cycles, right? Spanning cycles is 2 regular, 2 connected. Cycle is a 2 regular, two connected subgraph, right? So we consider this problem in terms of Hamiltonian decomposition as follows. So n equal to mk, k greater equal to 2, can Qn be decomposed into m copies of a spanning k regular, k connected bipancyclic subgraph? And see, instead of diameter, we consider connectedness and bipancyclic properties. And this is a generalization of Hamiltonian decomposition, because Hamiltonian decomposition is a decomposition of Qn into spanning two regular subgraphs, which are cycles. Here, spanning k regular, k connected bipancyclic subgraph. And we got this result. Qn is decomposable into m copies of a spanning k regular, k connected and bipancyclic subgraph. So in fact, we proved a more general result. This result we have proved for Cartesian product of even cycles. And proof goes by induction on k. So k equal to 2 follows from Hamiltonian decomposition given by Alspach and so on. K equal to 3 case, we obtain from the following theorem, which is analogous to the result of Aubert and Snyder. See, recall that theorem. When G is a 4 regular graph, even order, decomposable into 2 Hamiltonian cycles, Z is an even cycle, then Aubert and Snyder says G product Z can be decomposed into 3 Hamiltonian cycles. We say these can be decomposed into 3 regular, 3 connected subgraph, 2 copies. Moreover, G bipartite, then H is bipancyclic. So this is crucial result. So using this, just we can, the way Alspach finish the proof of Hamiltonian decomposition, we finish the proof of this result. So this 6 regular graph, this graph G product Z, this is 6 regular graph. We decompose it into 2 copies of 3 regular graph. So 1 copy I have suggested here. So G is C1 C union D product Z. So C becomes copies C1, C2, C3 up to CR. So these copies of CI we are joining by matching this way. Alternatively, edges are using here somehow. So odd edges are given for C's and even for D's and so on. So this is a way. So I'm not explaining all this, but this is a particular 3 regular graph. It is a type of honeycomb toroidal graph. So there is a paper of Alspach on honeycomb toroidal graph, which are particular types of three regular graphs, and it is of that type. And now, see, here we have talked about when n is multiple of n. So this is k plus k plus k plus k plus k m times. Then we are decomposing Qn into m copies of same graph, k regular, k connected bipancyclic subgraph, right? Now instead of taking all parts k plus, you take partition of n. This n equal to n1 plus n2 plus dot 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 nk, each ni greater equal to 2. Right? Okay, ni can be even. I am assuming at most 1 ni odd. Then Qn can be decomposed into k spanning subgraphs h1 to hk such that each hi is ni regular, ni connected. See, we are decomposing Qn as per degree partition here. But something we are losing here, this hi may not be isomorphic, definitely, because these ni's are not same. Further, we are getting only ni regular, ni connected. I'm not saying HI is bipancyclic. We are losing here bipancyclicity. However, when K is 2, we have proved that HI is bipancyclic also. But for general K, we don't know whether HI is bipancyclic or not. But for particular K, when K is 2, you can force HI to be bipancyclic also. Right? Then that generalize for K equal to 2 case generalizes the case of Yashwant, and this general K generalizes all those theorems about n equal to m. And then we tried this to extend for other variations of hypercube, and we got this. So we extended this result for the Cartesian product of even cycles, and recently, I think in 2020, for the class of augmented cubes. It is little difficult here. It is 2n minus 1. It's more complicated variation, but somehow we got similar result here for this class of graphs. But again here, ni's are even, at most one ni is odd only. So one can try this problem in general. So one can remove the condition of evenness. And this problem is again widely open for the remaining cases. And then using cycle decomposition of hypercube, we also proved recently what is this sunlight decomposition. So sunlight means, for example, consider a CK. Suppose this is 5 cycle. Add pendant H to each vertex of CK or C5. We call it is, people call it corona graph. Some people call it sunlight graph. So it is sunlight graph on 10 vertices. So from CK, you get sunlight graph L2K. And we proved that if Qn decomposes into CK, then it decomposes into L2K. So sunlight decomposition can be obtained from cycle decomposition. This is recent result. This is paper is communicated. Some smaller kind of results are obtained, but general results are still not published on sunlight decomposition of Qn using cycle decomposition of Qn. Okay, so this is all from my side. So references I will show. So this is an important survey paper from which I got motivated to work on this. This is the paper I was talking about, recent paper, which covers most of the cases of cycle decomposition. So this is a paper of Borse. These are our papers on degree-based decomposition, M factorization. And this is the paper I was talking about, decomposition of augmented cubes into regular connected pancyclic subgraphs. This is a recent paper. And few more papers about cycle decomposition. And this sunlight graph, this is a small paper, and this new paper is in the line. Okay. So thank you.
Let's thank the speaker.
So this is my university's main building. It is a 411 acres area. Okay, thank you. Thank you very much.
I'll stop the recording and then we'll take questions.